Okay, so we always like to start, 10,000 foot view. So that's right here on the, we're just zero timeline for patterns physics. And that is this, I already had it open, so I switched tabs to it. Uh, Here is the year in a single image: patterns, texting and driving, engineering and energy. So that's what we're focusing on today. But to just say the whole arc, engineering a shoe is what we use to contextualize forces and momentum, waves and technology around doing the most of the good stuff with the ultrasound and cell phones. And our culminating unit, electricity, power production, and climate science, that's around making a 50-year energy plan. And I say culminating just because space in the universe is a great way to end the year, but just so you do know it and hear it a couple times, that is 3 separate 2-day lessons that sometimes if you have a couple days before winter break and you want to use that, those are modular enough that you can put them in. They're optimal together, of course, but just trying to give teachers options. And so again, unit 1 is light on the performance expectations, heavy on the science and engineering practices. Unit 2 had just one performance expectation, and unit 3 is building up. So uh, now that most ninth graders are getting ready to handle these performance expectations that are really meant for end of high school. But of course, we can't wait for the end of high school to assess all of these. And so we have create a computational model to calculate the change in energy of one component in a system when the change in energy of another component and energy flows in and out of the system are known. I don't know if that's a good idea for me to read it, but I'll just finish that out. Use a computer simulation to model the impact of a proposed solution to a complex real world problem with numerous criteria and constraints on interactions within and between systems relevant to the problem. So that is the contextual basis for our bungee jump project. So hopefully you can see a strong connection. And so now I went to the unit 3 website. And again, this is going to be majorly revised based on that well-rounded access program, the feedback we're getting from teachers, NGSS writers, had a chance to talk with some people heavily involved with Open SciEd, and they said one of their jobs was to put themselves out of business. And so they were very open to sharing resources and things like that. So that's a great thing. But to transition for us, here is those performance expectations, here's assessment opportunities. And we really mean, sometimes possibly a new teacher feels like they got to do every single one of these. These are opportunities, and they really are assessment for learning. So if you might still do the activity, but it does not have to be entered into the grade book. There's a number of reasons why you might still do the assessment opportunity without entering it into the grade book. Those are really just meant to be exactly that, opportunities. So let's go and do an overview of the project. And actually, I think I might be handing this off, so I
Yeah.
will throw it over to Matt.
Yeah. Thanks, Bedford. So, yeah, we this whole unit is based on the idea of actually students performing a bungee jump with a doll, and we're going to model lots of good science around that storyline. How can we make STEM, or how can we use STEM to make a thrilling experience safe? And the overall arc is, and we're going to get into some a little bit more detail for each of these, but just want to begin with the end in mind, that students are start by tracking energy and are exposed to the problem really early on. Have some background with interacting with different types of energy and tool of science that we use, energy bar charts. Then we get into that second loop there, which is our system analysis. And this is the second time that they have completed a system analysis right after the texting and driving unit. And it's a way to think systematically about our problem and think about all of the individual pieces that go into coming up with a solution. ultimately they are posed with the demand to create an app or a spreadsheet that will predict how much rope to add on a bungee jump for different riders or jumpers or different sizes. So once we have that system analysis, we use that system analysis to look ahead for the rest of the unit and think about and use that for all of the things that we don't know. Of course, we need to do some more research or do an experiment to figure out. So we find ways to model kinetic energy and gravitational energy. We do an experiment where they investigate a bungee cord to model the bungee jump and see how different masses, ultimately different stretches, affect the elastic energy. Then they use computational thinking from equations that they created themselves, or they found themselves through experimentation and modeling. They come up with a spreadsheet and they create a spreadsheet. And of course, we have supports to make that possible that will allow them to predict and make a safe bungee jump for their jumper. And then finally, we end the unit with the bungee jump, a performance task bungee jump where they are using the bungee jump and they are interacting with at either administrators or volunteers that you have come in class to actually use their app to make those predictions. So big arch of our unit is looking at all of those things and coming up with that app. So what we'll do now is kind of look at our agenda and then dive into this project here.
Nice. And yep, the agenda's kind of overwhelming, but the good thing to know is it also provides a map of what we're talking about here. So this just shows point by point all the major points that we're going to try to make during the webinar. So really maybe think of it as a compendium to the app. And I actually want to avoid listing those. So we'll hop back in and maybe I'll actually, since the agenda follows the unit, I'll scan the teacher calendar. And this is going to be revised based on so much teacher input. And we're so appreciative and want to keep that coming. But in any case, here's just that big overview, a little bit of what Matt already said, the establishing of the project and learning to track energy into the system analysis. And we got a new revised system analysis that's a lot of positive feedback on exploring the models and including elastic. Here's a little touch and we're going to say it. So this is just the overview. In Unit 5, they need to be proficient at evaluating published materials. We have just so often found that students are not ready for that just like so many other pieces of this curriculum, they need exposure, practice, mastery. And so we start actually in Unit 2, evaluating materials. This is Unit 3, and it's getting more sophisticated. That doesn't even have to be entered into the grade book. There was some questions of, we do want to give students feedback, so maybe you do. But in any case, then there's the elastic energy model that was already mentioned, and then putting it all together, utilizing computational thinking and engineering to contextualize that, tracking the energy flow during a bungee jump. So to hop back, I'm going to actually close this now because we got, my screen is giving me more options. Okay, got it. Yes. That is actually kind of a really cool feature, but that is not what we're here for on this webinar. So the Extreme Bungee Adventure, Matt mentioned this. We want them to start the storyline. So everything there's a context. Why do we have to learn this? One answer is that it is to solve the storyline. And another, well, there's deeper answers too about making explicit how students are really growing through this unit. What are the practices? Okay, to keep that very straightforward, actually, I was going to try to make this bigger. it is worth actually just pausing and letting you read this, because that is exactly what we want students to do. Always a little hard to know how much time to give for that. There's a lot of intentionality in every sentence there. So I hope through the webinar that we kind of make that clear. But the two possible jumps is so that they have a opportunity to troubleshoot such a valuable skill, and then going into the final jump. So they don't just theoretically try to figure something out and go for the jump. This yellow here is so that you can change this to be what date you have planned for that final career expo day or app expo day. All right. One last piece though is here is a graphic, and we do switch graphics every unit. And in fact, that's even a question that we put to students. What do the different representations of the engineering process emphasize and not? And it's very approachable. They're coming off of unit 2, having already done a lot of engineering. But in any case, it's very important that we come up with a problem definition, and that's going to live on the front page of the packet. Yeah, we do have it right here. So front and center, what are we doing? We want every student to know every day, what are we doing? Right there, front and center on the packet. And very similar to texting and driving, how we develop it, that can be collaborative from your student developed. There is some benefit to you as a teacher to have one that's pretty similar across your different periods, so that you can have that written up and on the wall. If different periods, are enthusiastic about very different ones, you just might have to have a couple up on the wall. That's a good problem to have. And but in any case, it does not have to be exactly this, but the closer they are, just the easier it is for you as a teacher to have it up in the room. So we as app developers seek to create a user-friendly application in order to create a thrilling, safe bungee jump ride for Oaks Park. And that Oaks Park could be changed to a local amusement park too. So that does happen to be one that is local in Portland. Okay, and the thrilling and safe allows for trade-offs. That's, again, a lot of intentionality there. All right, I'm going to hand it, actually, I got this next part too. So we want to show you the phenomena and show you the driving question board and the revisions for it, that people liked it before, but they still were saying that some students were having it just wasn't as rich, and it to get everything they wanted, it had to be a little more teacher centered. And so we want to show some supports that allow it to hopefully be more student centered. And if that's not enough support, then yes, as a teacher, you may need to even go around and offer even more support. But hopefully these are ones that are allowing you to start with more and more student ideas. Okay, so there's a lot going on here. We are, I guess, actually, I'm tempted to cut to the short one, but a lot of students and a lot of teachers have even said that they like the story of this video and its Guinness Book of World Records, which is obviously a for-profit company doing.
So we're here today.
I'm sorry. Oh, well, actually, I realized there's so many things to think about. I need to stop my share and reshare optimized for sound. So let me get that going. No, not what. Sorry about that. Okay, there. I think make it full screen, and here we go.
At Bray Lakes to adjudicate the highest dunk of a biscuit by a bungee jumper.
So that is just a grounding video, right? They are doing their own, as Matt already said, they're going to jump their own water bottles, and you can tape on legs and arms that flap in the wind. It's super fun. There's some examples shown in the slides, but this one is a grounding one. What are all the things we need to be thinking about to have this be successful? So we want students, and again, I don't want to overpromise things, but many times we had it in many different classrooms and many different situations, many different districts, have students come up with a lot to almost all of the pieces. They need the teacher to facilitate that learning and even maybe facilitate the organization a little bit. But if you asked, what do we need to do as engineers? What do we need to know and measure, investigate, and model, right? That's still something that doesn't always roll off the tongue for students, but they're starting, this is unit 3, and they're starting to go, oh, what equations do we need? What mathematical models do we need so we can predict? Most students will say we need to figure out how much that bungee cord is going to stretch, right? So they can come up, they're not going to say the mathematical model, but they'll say we need an equation to figure out, or we need to figure out how much it'll stretch. All right, to understand and create that thrilling and safe bungee jump ride. So we used to just hand out Post-it notes with just this, and students would come up with almost, which is a good sign, and we still have it happen, that students would come up with almost the same thing because they're picking the most important ideas. So if you have 30 to 40 kids picking the most important ideas, they're going to come up with the same things, and that's actually a good thing. All right, so to add some more structure to this, we've broken it down into a multi-step process, which is very similar to what they saw in Unit 2. So just to be clear, they start with just verbally describing, right? Low barrier. They don't even have to draw or write anything. It's just verbally describe what happens during the bungee jump. Then in most likely a whiteboard or sheet, big paper, and a black marker, illustrate with pictures and words the important moments in the jump. Then using a red marker, they identify what variables that might affect the result. And so that would be like the weight of the jumper, how stretchy the cord is, how high off the ground. These are very accessible things for students to say. And one last thing I will say, in the workshop that Matt mentioned at the beginning, that would be, I don't know if, I'm assuming it's next week. It's almost always the following week. We will go and do this. So if you want more than the webinar, which is the overview, please do come to the workshop. Okay. And then just, so often to really give some students some feedback, right? Sometimes students are reluctant to say something if they think they're the only one thinking it. So Gallery Walk does a couple things. If you have a group, they're learning from each other. That's maybe the first thing to say about the Gallery Walk. This is students learning from students. It's also students going, someone else thought that was important too. And so we've just found that when students see other students having similar thinking, they might now actually speak. So just that's something to notice, so that sometimes if you decide to skip this, just know that it has multiple things. It's students learning from students, students gaining confidence about sharing their ideas. Okay, so in any case, they look at what other groups illustrated and find the important variables. And we're color coding the marker so that you as a teacher can kind of track, right? If you walk around and they say, oh, we've already put in what we learned from the Gallery Walk, and they don't have anything in blue, that's one indication. And so, you can just kind of catch people that I've already done this. And so it's a little bit of accountability. It's also something to celebrate. If students have a lot of blue, like, oh man, you really made the most of the Gallery Walk. So there's a lot of nuance in that you can build on here. I don't want to overwhelm someone who's trying to do every little thing. I'm just saying some extras so you understand the intentionality. And if you skip any of that, that's no big deal. Okay. Then this now, step 5 is what we used to originally do. So you can see we've added those 4 steps so that when it comes time to do the sticky note, that they individually describe on a sticky note what they need to know, measure, what they need to investigate, and what to create a mathematical model for a thrilling, safe one. And that unique one is they need to check with just their table. So it's not the whole class, but that way we don't have 40 students saying mass of jumper. That's good that 10 students, if you have 10 groups of 4, it's great that 10 students say that. That is a indication that when that student puts up massive jumper and then 9 other students come up to put their sticky note next to it, ding, 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 that's a very visceral, like, and it's also just like a positive vibe, like, oh my gosh, the whole class realized this. So that unique idea is that they are checking in with their table mates. So once someone at the table says massive jumper, they need to think about something else to know or measure. Oh, we need to know the length of the bungee cord. Excellent, that's unique. So put that one on there. So again, there's a lot of intentionality here to set them up. And then that's a much richer discussion. And it also is more expansive. It covers, you really can have 40 students put 2 or 3 sticky notes up. And after that, most of the time they've hit they certainly hit almost all of the big ideas and the tasks that we have. And oftentimes they've even hit some of the smaller ideas. Okay, with wrapping that up, I will hand it over to Matt to just any last comments on the driving question board and to take us forward.
Yes, excuse me. So yeah, the driving question board is a way for us to really explore, a lot of times explore the whole big idea, try to get all of the things that students know and know that they need to know to be able to solve our problem. And with that, Bradford, if you just click on the next tab, I think we like to use the calendar of learning sequence to really solidify what we did. So something as simple as, this would be in students' language, but what do? We use driving question board to broadly explore our problem and started to map out this. And then how's that gonna connect? It's, how we start working on big complex problems. We break them down into those smaller and more manageable parts. So born out of that is kind of some need to know, and we're going to give them a little bit of background in energy before we get into a more formal system analysis as it's coming up. So with that, Bradford, yeah, if you could go maybe just to the next slide there.
Yeah, and one last
go ahead.
I make one that this is probably selection bias. So we'll just say that teachers that do this report back it very valuable for students. And not every student will write this, but and again, we know a lot of teachers don't use this, but sometimes they say like students are wondering what they're learning. And this kind of metacognition moment is really helpful in that. So if you can find the time, try it out before. Try it out one time at least. Yeah, with that, I'll throw it back to Matt.
Yeah, good. Actually, can you head back to the agenda real quick?
Yeah.
So we started, and scroll up there. We started looking at like using that driving question board to build ownership and anticipate the big ideas. We checked in on our learning progression. Now we're going to equip students with some scientific tools and get them to start to use some scientific terminology to explain the situation that we're seeing. So the scientific tools, meaning energy bar charts in this case, really help propel students in their writing later on. So with that, go ahead and click on that. Let's see nope. Close out a couple tabs. Yeah, there we are. So you might be familiar with Energy Skate Park. Even some of my students had seen this in their middle school. It's a good way to introduce energy bar charts. My students aren't coming in with knowledge about energy bar charts and really explicitly thinking through energy transfers when energy is flowing from one object to another, and then transformations, energy that's changing within the object. And so we're not going to look at the activity too much, but it's in the packet. And it emphasizes a few things. Again, energy bar charts. It emphasizes energy transfer and transformation, but it also emphasizes conservation of energy through the app. Students are playing around with that, and yeah, go ahead, click on the packet, Bradford. And so it's in the packet. It's kind of a one pager where they're filling out bar charts. They're thinking about what they notice and wonder, doing some big ideas with stability and change, and then ultimately looking at a more complex situation with friction there. And so looking at all of those things together to really prepare them for what comes next with practicing with energy bar charts. After students are set up with that, set up with energy bar charts, set up with the ideas of energy conservation of energy, that leads us into getting some extra practice with energy bar charts, looking at how energy flows in and out or within objects in the system. So we'll actually maybe show a video of one of them, that the reverse bungee jump one, just so you get a sense of what that looks like. So I think there might be one extra tab in there, Bradford.
This one? No.
Yeah, that's just a quick warm up of a little bit later, looking at energy transfers and transformations. But yeah, go ahead, head to the tab to the right.
Okay, close this.
Yes, thanks.
Okay.
So this video is within a series of 4 or 5 videos where students are interesting. Mine can play on mine, so that might be an error on your side. So we don't necessarily need to show it. It's playing on my side. So students are some teachers like to give students a choice of where before and after are, and we're going to look at some key points on the jump for what's going on with the energy before a bungee jump and after a bungee jump. And in this case, it's a reverse bungee jump, and you can see down there in the speaker notes that the before is at the bottom while the jumper's still on the ground. After is halfway up when the jumper's still moving up and the spring is still slightly stretched. And it just gives students thanks Dave. Yeah, it's also in the chat, Bradford. I don't know if that one works.
Yeah, let me get that
chat. So it was given an error on Bradford's side. It's working on mine, but essentially we're looking at, yeah, there we go, a situation. And so this is a kind of a fun one to watch, like asking students, would you do this, and looking at that, and then ultimately pausing it like partway through the video and getting them to start to analyze and play with this. For me in my class, this looks like on a whiteboard, and maybe in pairs on a whiteboard, just to lower the stakes a little bit, because this is all new. Coming up with the energy as it flows in a system is very new for students. And so I always like to give them like a rough draft on something that's not so formal. And then when they bring this over to their packet, they are coloring in colored pencils. And Bradford, if you click on the key, I think it's right there. Yeah, you can see that we've color coded. Elastic energy is blue. That's kinetic energy going into on the right side, kinetic energy going into gravitational potential energy. We've defined those terms, all of the types of energy, and just giving students some practice playing around with where energy is flowing in and out and when transfers and transformations happen. But if you could just zoom in on it, on that one last piece that you're going to see on the quiz later is just the symbols for transfer and transformation. I just want to highlight that because it's a really helpful writing tool for students later on. When students see that like an energy transfer is that straight block arrow that's going to the left. Energy is transferring from the spring to kinetic energy in the person. and really being explicit about saying when that transfer is happening, and then it's transforming from kinetic energy in person to gravitational potential energy. So the curvy arrow for us is representing that transformation. And so those are really good things and details for us to add to there. And again, really like the process of going from, pairs on whiteboards over to the packet to kind of formalize it as it's a brand new skill for them. With that, they go through several examples, all different videos, and we're working on changing up those videos too. And ultimately, this leads to a writing assessment. If you back out and scroll down to page 7, Bradford, just on in the packet, if you zoom out. Or actually, you have the key open. Sorry, I didn't see that. Yeah, similar. Ultimately, again, students are using the tool of science, energy bar charts, to track the energy as it's falling through. And so you can see the different important positions along the way, the most important being the top and the bottom, and how the energy flows, from the jumper into the bungee cord in that situation. And maybe, if you scroll down, then they're using their diagram, and it's not worth our time right now to dive in and read, but they're using their work on those energy bar charts to help their explanation, thinking through step by step, what's the most important principle, the different positions along the way, and talking about that energy and transfer and transformation along the way. So that just helps. Those tools are helping us really take a peek and get those ideas across in there. And with that, maybe I'll hand it back to Bradford if you want to wrap up that and talking about the system analysis.
Yeah, excellent. And I'll show just one last slide that is, we really want, this is why we say use the tools of science to learn science. And one other story that we tell with this one often is that we went to language arts teachers and teachers on special assignment and asked, how do we have students write better? And they worked with us and said, what do you want them to write about? And that's really telling the story of this, of the energy flow. So going back to the performance expectations, and one last piece of the puzzle is to just ask students, how did you know that there wasn't kinetic energy? Oh, the jumper wasn't moving yet. Okay, good. Let's have them write that. So how did you know? They by this point in the practice, they'll make the energy bar charts pretty well. And then, hey, how did you know that it had elastic energy here? Oh, because the cord started to stretch. Excellent. So write that, because the cord is starting to, that's just like on paper and pencil, right on that packet. So the key didn't show that. So I just wanted to go over. They should in the packet be marking up. How did you know there was no kinetic energy? Right? They're not moving. Arrow EK equals 0. Excellent. And with that, then it's pretty easy to see that when we tell them to write, I'm going to back up. I wish I would have said this. What's the NGSS in one sentence? Use the big ideas of science to explain phenomena and solve problems. So here is an example. We want them to use the big ideas of science, conservation of energy, and tracking energy flow to explain the basic physics of bungee jumping. Okay, so I'll zoom in on this and just see. Now, this is an excellent level answer, and we actually just had another physics council member start for unit 2, a little bit of an echo, that we know that in the future, the key will start to have like a strong answer, a typical pretty good answer, and what's a typical way that students miss or misunderstand something. So that's another work in progress that is coming. But in any case, here is a strong student answer, which I hope you can see that using the tools of science allowed this student to write. So I'll pause, just give you about 60 seconds to read it. Okay, so here with this more grounded understanding of bungee jumping, now is when we want to iterate that driving question board. So we want the driving question board to live on, but now they can start to do some synthesis with it. Now that they've learned a little bit more about the basic physics of bungee jumping, they are ready. Although I don't. I want to get the system analysis. Okay, here we go. So now it is a process, and I think I didn't open the exact right tab. So they have that one paragraph description. And so I've opened the engineering portfolio. And again, there's always a paper starting from this unit forward. There's always a paper packet and a electronic engineering portfolio. And the portfolio is meant to have more polished things. And it also has critical information. So we just got this question recently about how can you just skip the portfolio? This is that same sentence that they already wrote, they already read. Sorry about that. Okay, and then we are showing you level 2 support. So students would have just a all black font, and that they would start to use some of the tools, either color coding based on, I'm going to try not to go in the slides. There's, color code things you must do, constraints, and then color code inputs, and that's going to be green, just like in texting and driving. If it's an input like speed of the car, okay, what are some of the inputs that we have to do with bungee jumping? Oh, somewhere you're going to have to put in the mass of the jumper. And they already know that, but it's also, of course, going to be in the design specifications of an app. But in any case, there's some very intentional reading and that will even peak in unit 4. But right now, unit 3, it's just a one pager. The first paragraph they've already read, and it's meant to feel a little overwhelming at first, right? We want to start to have students work through that. Oh my gosh, there's a lot on this one page. And then, okay, slow down. What's first? Read for understanding and start to color code things. And then, okay, all right, yeah. In fact, now with one page, I can start to move forward. And what is that? They're going to integrate this one page with the driving question board, ultimately to make their system analysis. And so you can just see that, well, this is the answer key, and that can look overwhelming. So I don't know, we got the packet key open too, but this is now really the next iteration of the driving question board. Remember the things they need to know. Now we don't want them just all over the place. We want them to be much more systematic. So it kind of makes sense that the starting height would be high up. The mass of the jumper is high up on it. And then I want to zoom out. What's the big thing? Here we're looking at energy analysis at the key moments, the starting position and the final position. And then there's all these little details. Yeah, it turns out if you're going to bungee jump, even just a doll or water bottle, you can't just know two things and throw it and think it's going to work. Yep, you have to attend to the mass of the jumper, how much string to add, the length of the cord, how stretchy, how strong the cord is, how much it stretches. Now, even though there's a lot of them, just want to point out that, again, students come up with all of these during the driving question board. They all know that the length of the cord is going to affect how far the bungee jumper goes. So there's a lot of them here. And that is the nature of project-based learning, that you really do have to attend to a number of things. The height of the jumper. A really tall jumper is going to need less string than a very short jumper. Okay, and then, all right, so that's good. That then just, this is really, I've now really thought of this as the next iteration of the driving question board, and it's now the map. The driving question board also served as a map, but now we have a very clean one. What are we going to do? All right, let's look at our system analysis. And of course, that is, I was going to say that's a cross-cutting concept. That's just really good for students to think, to wrap their head around the big problem. And I want to, well, I'm going to show this next slide. So it's out of order of the order I want to say it verbally, but I want to finish that thought. So we look at this. What do we need to do next? Where do you start? On texting and driving, we started at the top of the page and worked our way down. This also, we're going to start at kind of the top. But the first thing we're going to do is, all right, we qualitatively know that gravitational energy, it's all gravitational at the top, but we actually don't know how much that energy is. And it's not a big stretch for students to realize they need an equation. And of course, it's nice if they say, and some students might be at this point, not every student, we need a mathematical model. We need an equation for gravitational energy. So that's number one. And then, okay, massive jumper, we get that from the jumper themselves. Added string, I don't want to go into it, we'll go into the workshop, but you got to look at this for like 5 minutes for it to make sense. We can figure out the equation for added string right now. We can't get a number for it, but we can figure out the equation for it right now. And then the next thing that we can't figure out or isn't given to us by the jumper walking up to us is how strong this cord is. So we need to do an experiment on the bungee cord. And then the next thing, just working our way down, the next thing that we know is the distance stretch. That, of course, is going to depend on the spring constant. So that's really good that we did that experiment. But that is going to take another whole step. And of course, teacher talking this, that is the elastic energy lab. And then the final one is the ending height, that after they troubleshoot on the low height, if your final height's 20 feet, you might practice at 16 or 18 feet, and they are going to troubleshoot. This is a simple model. We are not accounting for friction or energy being transferred into thermal energy. So they need to deal, if they're going to really bungee jump, they got to figure that out. So that's number 4. That's that final one. All right. This is the perfect time to use our stronger and clearer protocol. And again, students always start off reluctant, but they are going to go into possibly the hallway, or it doesn't matter where you do it, but lots of times we do in the hallway, and they line up across from each other, this A, B, just across from each other, and they get 1 minute to say, and I'll just give a rough model. This is off the top of my head. All right, so in order to have a successful bungee jump, we first needed to do the energy analysis, and we figured out that the gravitational energy transformed into kinetic and then ultimately transferred to the elastic energy. So actually, we know from conservation of energy, the total energy minus how much is still in gravitational will give us how much got transferred in the core. That was hard to follow, so I'll give some simple numbers. If we started with 8 gravitational and end with 1 gravitational, we know that 7 joules of energy must be in the bungee cord. And with that, we can figure out the distance the cord stretched. And then if you look up here on my system analysis, you can see the added string, which is the thing that the operator at the amusement park is going to have to do. They're going to take the height of the person, the length of the cord, how much it stretches, and the buffer zone, and then they can figure out how much string to add for a successful jump. Okay, that was, yeah, I don't know if how authentic that was to what a student would say, but that is what we're going for. And then the student will compliment them on what they did well. And then the other student goes and they share their read of the system analysis. And they do that 3 times. And it is always a heavy lift, but almost always students feel better. They're like, I really did actually get better. So we don't want to overplay this one. We tried to do it just once or twice a unit, but at key times. But if students really understand the system analysis, they got the roadmap for the rest of the unit. That's why we used it here. Okay, with that, I'll throw it over to Matt to give some other comments on that.
Yeah, thanks, Bradford. We're actually gonna have a little bit of time to just like pause and reflect, actually in breakout rooms here. And so I've made breakout rooms of 3 or 4 people, just random rooms, and just want to give you some time to check in with a educator from somewhere else, possibly, and you're gonna basically choose one of the following to reflect on. So either the driving question board to start off a unit using the tools of science like energy bar charts as a pre-write strategy, or reflecting on the system analysis and how students might use that there. I put those in the chat, but I also know sometimes when you go into breakout room, the chat goes away. So that is number 12 there. And when you get into your rooms, if you don't mind just introducing yourself and saying maybe your experience with patterns physics and where you're coming from today, and just reflecting on one of those. Bradford, how long should we do for the breakout rooms? Like,
if we checking our time, I do think we give them what, 6 to 8 minutes.
Yeah. Okay. I'll do right in the middle there, 7 and yeah. So the breakout room is going to close right after 7 minutes here, and sorry, let me get one more thing done with the breakout rooms. Okay, I think I've got them all set up here. So again, you'll be in groups of 3 or 4. Just give you some time to check in and reflect a little bit. All right, we'll see you back here in 7 minutes. Oh, sorry, yep. Here we go. Oh, there's a bunch of people unassigned. How did that happen? Oh, you know what I did? Sorry, I'm gonna just assign a bunch of people. I made the breakout rooms before at the start, and it didn't assign a lot of people. Give me a moment.
You know, I have 2 monitors, you know that, right?
Oh, let's see. Here we go. Oh, okay. That was weird because I made the breakout rooms before. I'm gonna go ahead and pause the recording here.
You, Dave. I actually am going to keep it muted, and it just shows all, because I want to hit, they show a geosynchronous synchronizer, and they got a screen that shows data and people talking. And I'll just say, in one sense, a lot of teachers know that this is fake, but the one story I'll relate to is that is like lots of times we play videos that we totally expect students to listen to and believe. I'm thinking of like Veritasium, Physics Girl, Nova, National Geographic. I kind of got lost on my screen here. And they just listen, and students multiple times have said, look, those fake videos sound just like those other videos you tell me to listen to without questioning very much. So we just know, I'm totally lost. I'm going to go back to the agenda here to finish this comment, that we just know that students do need help with this. And, you know, in the workshop, dive a little deeper and just say that like the old things of like check for links, that go to a reputable university. The scammers have figured that out, and they have done all of those tricks. So the normal trick of just check if it's associated with the university, people have figured out. Does it do they link or reference a medical research? They do. So that's, I'll just wrap it up there, and I'm trying to get back. Okay, this is a particularly great one because there's also the video that shows, and actually this turns out to be an advertisement for high-tech shoes. And they have in the business section, just by chance, we had no idea that this was so local to Oregon, but again, it's not really the Oregon connection. There's an article that is in the video that said they got 9 million hits, and that was back, years ago. And they even said how they intentionally utilized things to get people to believe this. So that just shows how much they need science teachers helping them evaluate published materials. Okay, so to wrap it up, we compare a spoof, someone who skydives into a trampoline park, with someone who actually really skydives with no parachute, and which one is true, and they just watch either one. And this is meant to be a light touch. You could go harder on it, but we just have it as a light touch. And there's some good stuff about cross-cutting concepts. There's some discussion about writing a CER. They don't have to write the CER. I just want to make that clear. They're reading and thinking about how would you write a scientific argument about your confidence, or just evaluating published materials. So just to say it like it is. Okay. So we wrapped up thermal energy, which is an extension. It does come back though, right? When students troubleshoot and their bungee cord doesn't act exactly like they expect, they know that a lot of that energy very likely went into thermal energy. So again, at the end of the project, there's something very valuable for students that finish early. You can have them go and talk about the thermal energy, and that frees you up as a teacher to be working with students that need more teacher attention. Okay, so with that, we would come back and write. We now have the mathematical equation for EG, gravitational energy. It's really simply, we know this, mgh. Okay, so we have that now. That's excellent. And so we keep going, Okay, we now need to figure out the spring constant, the strength of how strong the bungee cord is. That's a word that students would use. All right, and then of course, we always want them to use words they understand, but also learn the technical terminology so that they can read a textbook, or they can go to college and hear the same words, or go to technical school. Okay, so again, using the system analysis as the roadmap, we realized we got to do the spring constant, and I'm going to lump 3 in here as well, the distance stretched. We need a mathematical model that takes this blue bar that we know is 7 joules in that simple example I gave, where there was 8 gravitational to start, there's still 1 in gravity at the end, so the other 7 must be elastic energy. So we know that, but we can't, from that, we need to get an equation to figure out how much that 7 joules ends up stretching the bungee cord. So that is our elastic energy lab, where we are going to try to figure out how does the stretching of a spring affect the elastic energy stored in it. And this oh yeah, go ahead, please.
Yeah. And so I actually want to show you a couple of resources that we have, and to be able to model this experiment a little bit better. And since we're not in person, we can't show you, but we do have some videos of the experiment to show that. But this is one where, just to set it off, and Bradford, if you maybe want to just stop your screen share, or you have 3C, I see that there. They are making their hypothesis, and we're looking at elastic energy. How does the stretch of a bungee cord affect the amount of energy there? And students are really able to, this is one that they're able to look at. We know it's either going to be proportional or quadratic. Those are we've confined our patterns to our 4 base patterns. And so really we're doing an experiment to try to evaluate how exactly does elastic energy look. And so, Bradford, I don't know if you, do you have the teacher calendar open?
I do. Yep. I'll
Do you
share
mind
my.
sharing that? Yeah.
Yep.
And so we've started making tutorial videos, and if these are helpful, we will definitely try to make more. But you can see where under the elastic energy experiment, it says investigation to determine math model of or how to take data for the spring constant, and then down a little bit, Bradford, where it says tutorial 2, where my cursor is there.
Oh yeah.
If you could click on that. This is just a video that kind of highlights, not worth showing the volume, but says kind of where we are and where we're going with that. And to show you the experimental setup, if you click on like right around 320, we're going to model this, and I'll have Bradford talk about the spreadsheet there. But essentially, what we're going to do is we're going to, you know, be dropping a mass on a string. You can see that the bungee cord's at the top, the mass is right there where Bradford's pointing, and we're going to be looking at how does changing the mass affect how far down it falls to drop. And so that's going to be that stretch of the bungee. So really changing that mass and seeing how those different things are stretching. Now, this was an experiment, and you can see like there's a couple of examples of changing the different masses, and of course a heavier mass is going to make it fall further as it's going. Now, this is an experiment that would have been almost impossible for our 9th graders to do without a spreadsheet. To analyze the data requires a couple of calculations before that to actually come up with the amount of elastic energy that is produced. And so students, use the system analysis, another version of a system analysis, to make a spreadsheet. And I think that's where, Bradford, you were going before I interrupted you. So maybe I'll have you talk about that spreadsheet.
Yeah, excellent. Thank you. No, that was a great interruption. So good. Okay. So I got to start closing these. Excellent. So we want to say that this is a multi-day lab. This is not a lab to just do a lab. This is where the learning happens. And this is the vertical articulation where they're doing system analysis. They've done it in texting and driving. They've done it for a bungee jump, and they need some reps. And so they are going to do system analysis again of that mass, right? Every student knows that when you put more mass and drop it, it's going to stretch it further. That is intuitive. We want to leverage that. And again, so here is the mass at the high point where the bungee cord is not stretched. And then the other key moment is the bungee cord at the bottom, stretched out. And I don't know if I want to go back. We always worried during the webinar not to switch tabs too many times. But in any case, this is very familiar. They have done this. And again, just exposure, practice, mastery, multiple times. They've done this many times. So now back in the lab, they're doing it yet again, more independently, hopefully. And so again, how will we get this? We just did that POGIL. You get the starting gravitational energy by MGH, and students really can largely independently do that. And then again, if you start with 8 and you end with 3, most students will say how much. I'm referencing my hand because we have those little toy jewels. If you're into that, we literally have little toy jewelry, and but that's on the supply list. People like it when they see it in person. I'm not sure if that works over the webinar. In any case, imagine if you have 8 jewels and then you only have 3, you know that the other joules must be in the elastic energy. So now write the equation for that. If you just say that, most students are like, I don't know how to do it. Okay, excellent. That is what we are trying to build. That is a real skill, mathematical thinking. But in any case, it's a two-step process. Okay, let's figure out. We know that the ending gravitational energy is mgh. And you know that whatever is not in gravity anymore must be in elastic energy by utilizing the big idea of science, conservation of energy. Okay, so they know that whatever you started with minus what you end with, that's what's in your elastic energy. We also, and again, I'll say students at first say, well, how much did it stretch? And students will go, I don't know. But we give them a little wait time and all of a sudden, oh, I can figure it out. Because if you know the starting height, I'm going to switch this meter. I'll stay in meters because that's what we do. So that it's joules. 1 meter high and it ends 0.6 meters high, you know it must have stretched 0.4 meters. So again, I want to point out that this is intuitive. It is not intuitive for students to write the equations about how they did it. And that's why this is pretty rigorous. They need to think through, but I just want to show that connection. They have done a lot of this work previously, but now they're actually writing the equations. And of course, this is getting them set up for the rest of the year. And it's beautiful in the sense that where do they go from here? They go, and I don't have the spreadsheet open. Oh yeah, it is. It's right here, pasted in. That's why you open the key. And they go and program, right? They have their system analysis, and that tells them, okay, if I have the mass that they selected, the independent variable, the mass, and they know the starting height, 1 meter, they put it at the top of the meter stick like Matt showed, and the ending height is 0.84, they can code. Well, I said I just ended up talking about distance stretched. You can code it. You know the distance stretched. And I'm missing I'm clicking on this cell, but it's not showing me what's in the cell.
It's in the, because you're in the Google Doc.
Oh, yeah, I'm not in spreadsheets. Thank you. So in any case, you would just see that it is the starting height minus the ending height. And of course, the starting gravitational energy is mgh. And so this would be coded as equals m, go over here to cell, whatever this is, and mgh. And so a lot of students get a kick out of that. That is very concrete and like very satisfying. So in any case, we can figure out the starting energy and the ending energy in gravity. And so we know the missing energy must be the elastic energy. And so now we can make a very straightforward graph around distance stretched compared to the elastic energy. And so we're then ready to answer, how does the distance stretched affect the energy stored in a bungee cord? And that is a quadratic relationship. And there's a lot of tools that we have to analyze this. So I want to show some of those, but I want to just point out that students see empirically, they see their data, that is quadratic. All right, so we know, yep, there's a lot of tools. So but first things first, I was going to jump to the pattern, but yes. So of course, data discussion, and we put out that data script and got sort of mixed reviews. And so, just having the whole script and saying read start to finish, a lot of overwhelming to some students. So you might want to be selective. Maybe you do some stuff as a whole class, and then when you get to similarities and differences, you switch over to the script, or maybe it's usually the C value. Some students can get it on their own, but a lot of students need the whole class discussion. So kind of maybe selectively use the script where you think students are ready for it. And, each data discussion, they might be more and more ready each time. But here's the card sort. Card sort is very approachable. Even a student that missed the lab can come in and organize the card sort. So that is a very low barrier conversation starter. So an excellent one to do. We just want to show, and these are all mixed up. intentionally in case a student sees the printout before you've cut them up. But in any case, they sort these out and realize that, oh, and yeah, I don't know how much to summarize the big ideas here, but oh, a weak spring, no surprise, a weak spring actually has the small number. And that kind of makes sense that a weak spring, if you stretch, we always like to put the same input, stretch everything 1 meter. Okay, well, this red one only has 1 joule. And again, Matt talked about it. They should have springs in their hand, right? We have all of that bungee cord, and students know that if you were going to get snapped by it, not suggesting you have students snap them, but they just know that if you pull a cord back, it's going to hurt more, aka transfer more energy to you. So you would not want to do that. And of course, if you have a strong bungee cord, it's really hard to pull back. You also don't want to get snapped. In any case, we want them saying all of those kind of things. We call that walking the triangle. And so they see in a graph that, hey, this red one, that's not going to hurt too much. You stretched it 1 meter, but it only has 1 joule of energy. This blue one, you stretch it 1 meter, it has 3 joules. That's going to hurt a medium amount. This one, stretch it 1 meter, it's off the screen, and you can even estimate maybe 4 joules. Okay, so we want students talking in a very accessible way about this data. And then that culminates with, why is it quadratic? And I just turned the corner with my own students that they now like it. And I had another teacher come in my room right as we were doing the choral responses, and they're not for everyone, just want to say that, but that they were kind of, being loud with it. And so I'll just say the choral response for quadratic. Some things in this world, when you double the input, 2 things happen. It gets twice as wide, it gets twice as tall. So the output, 1, 2, 3, 4 quadruples, we call that pattern quadratic. And my students have even now customized that to each time. So you do that with acceleration. Some things in this world, like rolling a ball down a ramp, when you double the time, 2 things happen. You give it twice the time to roll and twice the time to accelerate. So the distance it goes, 1, 2, 3, 4 quadruples. And again, we're going to see that same thing. When you have a spring and something's in this world like a spring, when you double or when you stretch it twice as far, 2 things happen. You stretched it twice as farther, and you stretched it harder. So the energy stored in the rubber band, 1, 2, 3, 4 quadruples. So it totally makes sense that the pattern with elastic energy is quadratic, because stretching it does 2 things. It stretches it further, just more cord is stretched. And we know from we've skipped it in the webinar, but they know that as you stretch, and they experientially know this before they even enter high school, that when you pull a rubber band, it gets harder and harder to pull. So want to say that that's, this thoughtfulness is grounded in student experience. And we want students to feel really good, even though, and that's super rigorous, right? I just want to review one last time, and I'm going to wrap up, that they did a small scale system analysis that allowed them to code spreadsheets so that they could actually directly plot distance, stretch versus elastic energy, and ultimately make sense that elastic energy is quadratic, because when you stretch a cord twice as far and twice as hard, the energy quadruples. Okay, with that, I'll throw it over to Matt to catch anything I might have missed and take us forward. And I see you're muted. Yeah.
Yeah. Thanks. And if you could just go to that next slide there, just to show, Bradford was talking about, the factors that happen. And so there, of course, are there slides to reference back to previous quadratic labs that we've done and connect forward to the lab that we're doing now with elastic energy. And then, of course, what do we do after that? You can go ahead, close that tab. We are going to put that into our system analysis. And we really want to, we're essentially done with our system analysis. We have gotten, we've looked at the energy, MGH. We have our spring constant. We know how elastic energy and the distance the cord stretches are related. And so we're really ready to put it all together in our system analysis and actually do the bungee jumps. So we wanted to show you some levels of support that students have to be able to do that. So we linked the calendar, and yeah, Bradford just scrolled down to it. So actually scroll up just so you can show this section. Let's see, actually keep on going down. Sorry, I was in the wrong section. Yeah, you were in the right place. So scroll up just so you can see the header of the task. So we are going to start using computational thinking and prototype testing. So really want students to make that connection. Everything that we've done in class has led to this computational thinking that we're looking at. And Bradford has highlighted there just various levels of support for coding in the Budgie Jump app. There's templates, and those templates are linked specifically to different video tutorials. And there's different leveled templates as well. So templates with everything filled in and a video tutorial associated with it, and everything from that to a blank spreadsheet. So we really do want students to take a peek and look at those. So Bradford, maybe just click on one of the keys there. Just to, yeah, maybe I'll go to this one. Yeah. And so students, I want you to see that this spreadsheet, there's really intentionality of how the spreadsheet's set up. It really does mirror the system analysis that we've done. So when you're kind of flipping back and forth, massive jumpers on the top, starting gravitational energy is there. All of the stuff that is on here, it's going to be mirroring our system analysis, and everything that was color coded, inputs, outputs, things that you need, all of that stuff is showing up in the system analysis as well. And we want that to mirror it. Eventually, students are going to take this and make it more user-friendly. And Bradford can show you, here's an example of one that's user-friendly, just putting only the important things at the top of the spreadsheet. Mass of the jumper, height of the jumper, those are important for figuring out the jumper, and then the string added. And then everything else is hidden behind the scenes in this one, where down below, in this case, they organize things with color and size to make the most important things really stand out in there. So all of that system analysis and everything there is leading up to this bungee jump that students are putting together this app, and then ultimately they are able to do that. If you don't mind clicking on just like that box set where your cursor is. There also in the slides is mock data for students to test their spreadsheet on. So when students are coding, sometimes they will just put in, they'll see on the video that it says 1.62, and they might just type in 1.62. This is a good check to see, are students are their spreadsheets working properly? When you change the input, does the output change? That's a really important step and important key for us to be able to check in and see, are they coding it right there? You can also see to the right side, there's tutorials on how to make the bar charts, set it up in a table, and show how the energy changes as the jumper falls from the 4 different positions that are on there. With that, I'm going to hand it off to Bradford and let Bradford talk to you about how we introduce troubleshooting and thinking about a quiz on troubleshooting before we actually go do the jumps.
Yeah, excellent. Okay, so troubleshooting is multiple. Like, that is a really great skill, and it's actually in the NGSS, in the Engineering, Technology, and Society standards. And, you know, we were like, okay, it needs to, students need to be assessed and given feedback on how they're doing with that. And of course, it just really sets them up for success. So we picked the two things they have to troubleshoot. You know, there's a situation here when helping a friend prototype test, their cord comes, or yeah, we obviously we do some work in class where it came up short, but to mix it up for the assessment, it goes long. And that's great because that is going to really happen. It's going to come up short or long, and it usually comes down to two factors. The mass that they put in was wrong, or they didn't account for the energy in the system, the mass, or the spring constant is wrong. And it's often the spring constant. I mean, it can be, if you just enter the wrong mass, it's going to go awry. Yep. So in any case, though, I want to point out that this is real computational thinking. So they use a app, and actually, we're close enough on time, but the webinar is just the overview. So in the workshop, we will actually have you try this and see, but they can go to an app and just figure out, it's so close, and I think we have the time, but we're really close on time, and we do actually want to give one last processing time. So I think in the workshop, we will go and actually do that quiz and do the troubleshooting. So if you're interested in that, please do come to the workshop. All right, but in any case, students can try out using the spreadsheet and actually use their brain and a computer to give them feedback. So I'll just actually, maybe I will show one time mass if it's 0.2, and let's say it was actually 0.3. Now you have to be looking at the stretch of the cord, 2.3. Oh yeah, it just jumped up to 2.5. Yeah. So if they put the mass in wrong and it went far, the jumper must actually weigh more than what was inputted. And so they can figure that out computationally. And we didn't show the key. So we have here, let's just go to that assessment and show the key. Because again, this is a very powerful thing. Like, oh, whoops, I opened the wrong. That's the homework key that I opened. Should have gone to assessment. And here's the key. So again, there's a homework practice on that too. But how cool is this? They are using screenshots from a simulation to argue from evidence about how to troubleshoot what went wrong with a bungee cord. And I showed a very simple answer. Students oftentimes figure out exactly how much mass resulted in that 0.2. So that is a pretty rigorous assessment. And again, I'll just get some external validity here that we were able to hire an NGSS writer to evaluate all of our assessments and got a lot of positive reviews about the 3D nature, the engagement with that. So that is a structured assessment opportunity to help students think through this project so that they can be successful with the final jump. So they're troubleshooting in the quiz that way right there. And then they go out and actually do the low jump, you know, let's say it's 18 feet or 4.5 meters, and they might come up short. The easiest way to fix that is kind of a hack, is just to mess with their buffer right here in this cell. That is the solution that makes it very manageable, keeps this 9th grade appropriate. If students are really need more challenge, and this would be unlikely your whole class, this would be a handful of students, they can go and add thermal energy into the mix. So, and they can estimate that at the low jump, how much that is, and give a rationale for why they are doing their buffer. And the support for that is in the engineering portfolio, which I don't have open right now. So I'm just sensitive to time here. So, but yes, that is supported. And again, that this is a critical feature of the curriculum. There is good stuff built in to have students that need extra challenge. And part of that challenge is that they are more independently doing those things, which allows the teacher more time to spend with students that need more teacher attention. They're struggling for any number of reasons. Lots of times the best resource, even better than level 2 support of the portfolio, is the teacher coming over and able to talk with them. So that is a intentional structure of the curriculum, is to allow to free up the teacher to actually go and do that. So I'm going to close these. Yep, here's another support. There was some roles in this. And again, as a first year implementation, that's probably one more thing to track, which I don't know if that's helpful or not. So that those are explained in the engineering portfolio. But in any case, here's a very clear steps. If you are the app expo manager, you need to make sure to do these things 1 through 9. And if you were the experimental manager, you need to do these things 1 through 10. This is pretty neat. I don't know if this is a first year thing or not, but we do have it all set up that on jump day you can invite teachers and admin, possibly parents. And this is a sheet pre-made. Like, this is almost ready to go. You just got to print things out. Now, the one thing to say is sometimes people that have not been around teenagers sometimes have unrealistic expectations. They get frustrated that the teacher didn't make or the student didn't make eye contact or something like that. So there does need to, administrators and other teachers are pretty familiar with that. So that might be the place to start the first time. Okay, but in any case, here it is. Your principal comes in and you give them the jumper, the water bottle, and it will say 0.1 kilograms and a height of 0.28 meters. And they need to walk over into the student's Chromebook and type that in and get the answer. And you can imagine that if they saw this one, that would not be that user friendly. Where do I put this stuff? But if they saw this one, they would go, oh, that was pretty easy to put in the mass and height and read out the string added. Okay. So those questions are, whoops, so many tabs. And then they have these questions. Software manager, who is that? Oh, nice to meet you. Can you explain the physics of bungee jumping? And students knew that they were getting that question asked. That is in maybe at this point, I will open up the portfolio because I've referenced it several times now, and I'll show where each of those things are in. So I am here and I want to open the engineering portfolio. So here is the engineering portfolio. I'll just click on that. This is one more time. So again, here's that one pager that we started the unit with. Here's those 3 positions that are optional, but if you like that, it is a fun thing. It adds a little more structure. And usually there's groups of 4 and someone's absent. So there's 3 roles so that if you have an absent, someone can fill in and not have to like break apart the room or break apart the roles. Again, here's the final polished statement. Here's that quiz, explain the basic physics. This is where they would put a picture of their system analysis. Here's that mini lab for the spring constant. Here's that extension that I talked about where students could add and track the thermal energy in the bungee jump during that. And then here's where they put in a screenshot of their final software program. And then here is very understandably evaluate strengths and weaknesses and reflecting on STEM. And this is yes, iterated to the evidence statements and really bringing in the cross-cutting concepts. So that is another thing we're getting from the NGSS writer, that lots of times we're talking about at the practice level, like we say, just asking questions, but asking questions, you can ask questions at a 4th grade level, 8th grade level, and a 12th grade level. You can develop models at a 4th grade level, 8th grade level, 12th grade level. Okay, all that good stuff, but just want to show that that intentionality is baked in to the engineering portfolio. So this is that reflecting the strengths and weaknesses and the benefits of using system models, you know, that cross-cutting concept and limits. All right, with that, I think I threw in a couple extra things there. I know there's a couple other things to say, so I'll throw it over to Matt to hit some of the points that I skipped over, and we'll start to wrap up.
Yeah, thanks, Bedford. So, you know, we were talking about, you know, jump day, and there's just a couple of tips to think about for, you know, supporting students during the jump day. It's really helpful when we go. If you have another teacher who's teaching physics next to you, you could go at the same time, or having another adult, you know, actually do the jumps for you. So we've had admin come out and actually drop the bottles for us while we're, you know, helping students get situated. In the on the teacher calendar, there's some fun awards and signage in Bradford. If you don't mind just clicking on the teacher calendar, like scrolling down to the bottom, you know, so right there, there's just some fun, some signs and some awards. If you want to do that, those, just having like a station, just so students are ready to go. You know, they go from one place to another. So you have the bungee zone where nobody should be walking. There's an interview station where they're going to be at, you know, measuring the weight and height. They're going to measure the string added, and just kind of operationalizing it so that you can get through all of the groups when you're doing that. Another key is just finding a place in your school that that's going to work. And so we've done that in workshops. We've done that just from chairs in the classroom. We've done that off of a ladder, or at our school we have a balcony. So just finding a spot on the stands or somewhere where you can look at that. Last is that one that Bradford just had open. If you are dividing the task up into different roles, this is just like a self and peer evaluation that just kind of adds a little bit more of that accountability to the experiment as you can. And again, maybe first year you don't divide up into those roles, just out of another thing to keep track of, but those resources are there for you as you're doing those jumps. Last thing I just want to reiterate is testing on a lower height before the actual jump day is really helpful. Just gives feedback for students of what they're going to do. Again, sometimes we do that from just in our room, or from a hallway, like a stairwell that's a little bit shorter. That just gives students the feedback of like, do they know what they're doing on measuring the jumper, height of the jumper? Do they know how to measure the string added, and ultimately how to do the drop? So just some helpful tips and things that are there. There are also on the teacher calendar, Bradford, can you go back to that? Just some in the materials there's like right where you're at, scroll down, back down. There's just we've used water bottles. So if you click on the one there, Bradford. Just to show you examples. So we've used dolls or action figures. We've gone to using water bottles, and it kind of gives there's some helpful tips in the teacher notes of like how to determine those variables.
And there's several questions in the idea capture tool about like how much. Here it is recommended. You know, it's pretty light, right? The more energy you add into the system, the more energy it has to deviate. So those are not full water bottles. That is a very challenging jump if it's 500 grams. Excellent. I think we're just too, this is actually a good spot. We were going to try to put you in breakout rooms one last time and then try to answer all of the idea capture tool questions. I think that was going to be short, but I think it's that's good. So we want to give you time to do the exit ticket during this time. So I think actually we probably wrap up pretty close to here. And that is the those were the highlights in the webinar. So again, if you are interested in more depth, we do have the workshop, and that does have where we will actually, you will code a little bit during the workshop. So if you want that level of detail, please do come to the workshop. Here is the exit ticket, right? This is grant funded. And so it's really important to make sure to provide evidence that this is actually having an impact. So if you wouldn't mind, it's kind of familiar routine, and it is a lot of the same questions, but if you could just take these last few minutes and fill out the exit ticket, we'd appreciate that. And if it's the right fit for you, hope to see you at the workshop next week. We like to end with our 3, 2, 1